why and how do we make machine learning reproducible, especially for scientists? Well, so we can make a huge impact with machine learning. Essentially, we have the ability to make things faster, do things that were never able before. Like right now, everyone is wild about stable diffusion, where we can write a sentence and then suddenly things appear, like images are generated. And of course, every scientific discipline has machine learning workshops at the moment that are just like, oh yeah, and you can do this and you can do this faster. And these revolutionary insights are possible now, like the protein folding that has been done. So we can really do things that were never possible before, which gives us, well, great power, but also great responsibility. And of course, we're doing science, there's scientific results, and in theory, scientific results should be reproducible, but the reproducibility crisis has been ongoing even before machine learning, but machine learning really has the power to exacerbate that and make it worse. And we kind of don't want that, but if this was like, we're scientists, we should do that. If that was the only reason, then yeah, we wouldn't have this workshop or a lot of other people talking about this issue. So what are other reasons we want to make it reproducible? Well, human progress. So if we build our model and we do this cool thing and people can take this model and build upon it, that means we are now progressing much faster because they don't have to figure out how to do this from a abstract paper. I think everyone here who has been working in science or machine learning has seen those papers that are just like a vague description, which often is just a nice narrative around how this model could have been built. So you have no access to data, no access to the weights, no access to the training scripts, and that's a nightmare to reproduce. And of course, ethical work. We have to check that our work is ethical and can, doesn't negatively impact everyone involved. And reproducibility really helps there because it's adjacent to open source work where we can really have a look at what is the training data, how were these models conceived, and yeah, what design choices were made in these models. And of course, funding bodies will want this more and more, especially if you have like this black box model and you say, oh yeah, I found the scientific insight, and just say, oh yeah, and that's it. A lot of funding bodies aren't that happy with it anymore because there's like a divide between the engineering and the progress, and most funding bodies want to fund progress in science and not just this one thing that you can then build an API around. So there's that requirement that is happening more and more. And of course, it's easy to reuse. So that is, other people can use it much easier if you make it reproducible. This can build companies, this can build more scientific impact, like I said before, with the human progress, but it's also a gift to ourselves, because if you've ever gone back to your code and like just a year and look at that code, a lot of people despair. I have despaired before I got better at these practices to really, well, build better models and write better code to make it reproducible. So bad machine learning and bad science unfortunately hurts people. So we have to work to make these models as transparent as possible and make them reproducible so people can check the work, but also people can use the work to then go on with it. But how? Like, that's big words, and I myself have been struggling with this a lot. Like, how do you actually do this? Well, we can start with a model evaluation. I won't go too deep into this to not step on Valerio's toes, but essentially we have to ensure we have valid results. If we don't do proper evaluation, like, for example, if we just train on the entire data set and we overfit the model to the data set, write a paper based on that, that means we now have a paper that hopefully doesn't get accepted because reviewers should reject that. But this paper has taken, first of all, a lot of work, obviously. So if it gets rejected, that's sad for us because we put in all the work. But also if it got accepted, that is now a scientific result that reports, oh yeah, we can do machine learning with this on something that actually wasn't possible, because the overfit model actually doesn't generalize to new data. It's just on this data set, this subset of the actual world, of the real world that we're looking at. So we have to reject this to be able to, well, work with actual insights. And of course, we can reduce the impact of like dependence with model evaluation. Like I have a nice image of a satellite here, and if you use satellite data, it's dependent spatially because we have maps essentially, and it is dependent in time. So we have to look at that in model evaluation, and of course address real-world class distribution. Rarely do we actually have like homogeneous classes in our data, but that's enough about that. So how hard is that? Well, Valeria will talk about it, and I wrote a mini ebook that you can get on my website for that. It's free if you sign up to my newsletter. But essentially I go through all this like in one page for each of those. And of course, we have our GitHub repo where all of that is documented with code. Valeria has put in a lot of work to make this Jupyter Notebook really high impact. So the next one is benchmarking. For collaboration, this is really important. We can use dummy classifiers as the basis and use domain solutions. Like in weather, for example, we have Weather Bench, where we have the specific solutions and we can then compare it against each other. That is part of reproducibility, where we can actually compare results on a set of data where we can define the metrics and really say, okay, your new insight should be able to work on this. And yeah, benchmark data sets like that. And of course, simple models are really important. Like compare your model to something that isn't a deep neural network. We had this paper in seismology where this huge deep neural network was published in Nature to predict something about earthquakes, I think the aftershocks. But the problem was you can do that with a linear regression if you just don't take the important features. So we really have to use benchmarking to be able to compare that. And domain solutions also means like use solutions that already exist in the domain. Right now we're working on a paper where we have a really cool transformer doing a thing in weather forecasting, and of course we have to compare that to existing solutions. Like there's a member by member solution that basically shifts all the weather forecasts individually, and that is like a very good approach, like a very advanced approach. But if we compare our machine learning model to that, then we can actually say, all right, we're doing some good work here. So not just the super simple models, but also like domain solutions that work. And of course, yeah, random forests are my usual like baseline model because they're non-linear. They are usually a little bit better than linear models. But yeah, if a linear model works on your data set, you certainly don't need a fancy big model. So model sharing, really important. This is also part of later talks as far as I know. But yeah, you have to export your model, share model checkpoints, fix the sources of randomness. This is really important. Like PyTorch and TensorFlow and scikit-learn all have a specific web page about fixing all the sources where stochasticity comes in. And it can be a little bit more tricky because you have to fix it for PyTorch and then for NumPy and maybe even for Python, depending on which version you're on. So going back to the documentation for this is really important. Then linting, formatting, use automatic linters, I'm a fan of black. I know some people don't like it, but like there are also, I think there's like dark and gray and blue that are taking some liberties on the black formatter. So you can make your code really looking nice and standardized according to the Python standard. That really helps in sharing your code with others. Like, even if your code isn't the best written, because we're all like scientists or researchers, so our code isn't to the standard of a computer scientist that has written their entire life in C or whatever, but we can at least make it easy for our colleagues to also read the code and then work through the code. And yeah, doc strings are a really nice way to document actually what you're doing, and you can build a documentation out of doc strings, so using those. And if you work in VS Code, which I love, you can install an extension that basically writes most of the doc string for you if you have type hints. So it just goes through your function signature and writes most of the doc string for you. So you just have to write the description of the actual inputs and outputs. So makes life really easy. And yeah, I worked with a developer that was in Java before who hated writing doc strings, but when I showed him that one and another extension that actually uses machine learning like CodeBird to infer what the variables might be, then doc string writing becomes really easy, and your colleagues will love you for it, because even if they use Jupyter notebooks, they can just shift tab into your function and see what it's doing. And yeah, of course, fix your dependencies. This was actually funny when Valerio did the first pull request on what I had written before. He fixed all my requirements files because I was lazy. I just had the name of the thing in there, and now we actually have versions in there, which is the much better way to do it. But yeah, so start at least with sharing requirements files or an environment YAML, but if you can pin the version of it, then it's even better, especially in machine learning, because I have seen some research where people were doing all sources of randomness were fixed, and they just ran different versions of LightGBM, it was at that point, and you got different results. Just because the version differed. So fixing the dependencies is really important for model sharing as well. And of course, the golden standard is Docker, which can be frightening a little bit. But we do have an example Docker file, which doesn't have to be that hard, to be honest, in our GitHub, so you can check it out and see it. And there's also people that try to make it even easier with the whole sharing. And then of course we want tests, but we have a talk on that. So I'll just go quickly through it, like fix all your inputs and see that your methods are working deterministically, take some data samples for tests, do doc strings, because you can write examples in doc strings, and then you can do the doc string test, which is really, really neat. That's like the easiest way to write the first test. And of course, validate your inputs. And yeah, interpretability is it's a two-edged sword in a way. Like, there are some interpretability methods that have fallen out of favor a little bit because they only interpret one sample. So they are nice for publications because you can find the sample where your network looks the nicest and say, oh yeah, this is explainable AI, but it just explains it for one sample that has been run through your model. So yeah, but there are tools that are good. Scikit-learn has some of them, like the permutation importance and partial dependence plots, which really explain how important a feature is, which already is an interpretability tool. And I've used it a lot in my work, where I work with domain scientists and really try to work together with them to be able to, basically build something together and show them how the model interprets their data. And that is a good like sense check to see if the model puts importances on the important, like the domain expertise important features. Then you can use SHAP, but I have a love-hate relationship with SHAP at the moment. If you are on Discord, after Ian Oswald's talk, I was saying it's low-key unusable right now. There are a lot of problems with the dependency, and I think there is only one developer on it at the moment. So it's a little bit, if you can make it work, it's amazing, but right now it's not working out of the box, which is sad because it's such an amazing tool and it used to be so useful, but right now it's just, yeah, a little bit bug ridden. But when that comes back, definitely use it. Use model inspection itself. So see what is going on in your models, and yeah, then communicate results. So make sure that you can build a good rapport with domain scientists so they can actually understand what you're doing. No one is actually interested in your accuracy number because you can also use it to cheat, right? 99% accuracy doesn't mean anything if you don't know the data. But be sure to build trust, essentially. So you want to build that intuition about the model, about the data, and build a good rapport with domain scientists. And then the last one I am quite fond of is ablation studies, especially if you publish your models, because we all know in data science, a lot of is very iterative. Like you try this, it doesn't work, then you try that, it doesn't work. So we kind of follow this optimization path, but we don't know if it's the optimum, if it's the best model for everything. So what we actually do is we remove components from our solution in the notebook. I've been cheating a little bit because we have such a toy model that I didn't build a deep neural network where you can switch off like your probabilistic part or this part. So I just switched off the standardization to show that you can show that the standardization was really important. So it's a mini ablation study. It's kind of cheated, but just to show an example of switching off different components in your machine learning pipeline, in your workflow, so you can actually argue that this was important to include. And yeah, that it's not spurious in the end. And yeah, that shows the impact of your final pipeline. So where do we find this? Well, our website, realworld-ml.xyz, where you can get the GitHub as well. It should also be linked in the page that I never got your name, our moderator. Sorry about that.
Sorry, it's Kevin. Yeah, sorry, I was at the chatting away at the start. I'll just put some details back in the chat there.
Oh, fantastic! Thank you so much. Yeah. So as Kevin showed before, on our talk page, it's as well. You can also access the talk page through the website. But yeah, if you make it easy to use, people might use it, and I think that's the actual thing, because then people cite you, then people build on it, and you're doing actual science and not just some weird thing that no one can use in the end. So thank you for your attention, and that's it for me for this overview.
Fab. Jesper, there's I think a question. Do you want to take this right now, or do you want to take it later? There's a quick question about Faceit as an announcement for SHAP.
Oh,
it's in this. I can read for you. It's from Haid saying regarding SHAP interpretability, there was a talk earlier today on Faceit 2.0, which seems like an announcement of SHAP.
Oh, well, that's awesome. I'll have to look at it. I haven't heard of it yet. And if it's built on top of SHAP, I'm a little bit skeptical because SHAP is not in a good place right now. But there are a lot of other libraries as well. So there's Alibi, there's Quantus. A lot of people are trying new libraries for explainability, especially of CNNs, because yeah, I think there's also layer-wise relevance projection from the Fraunhofer Institute, which we've been using, and it's really, really good for that explainability. But yeah, thank you. Awesome. And I think after me, it's over to Mike, right?
I think I should be going, but
oh no, yeah, I'm missing it. You're going. Thank you. Sorry.
Yes. No worries, no worries at all.